Module 5, Lecture B, Capstone Case. By the end of this lecture, you will be able to build a complete Python program that processes a small medical dataset from input to report output. Evaluate the program for correctness, readability, error handling, and appropriate handling of sensitive examples. And present the workflow results in a concise form that supports clinical or research interpretation. Integrated data workflow. Data input pipeline. A reliable data input pipeline is essential in medical data workflows because it controls how raw data enters a program. In Python, health data from files such as spreadsheets or CSVs must be opened, checked, and interpreted before analysis. The goal is to confirm that each file exists, can be read, and has the expected structure, creating a stable foundation for later work. In medical computing, responsible data handling begins as soon as information enters the pipeline. Dates, numbers, categories, missing values, names, and sensitive content must be checked so they keep their correct meaning. Early validation helps catch inconsistent entries, unexpected columns, odd encodings, and problematic values before they lead to misleading results. A strong data input pipeline makes analysis more reliable by defining the data source, format, and assumptions before processing begins. It protects privacy by working with de-identified or synthetic data and limiting personal details. By summarizing records, fields, and missing values, the pipeline helps confirm data quality and supports clearer testing, explanation, and reporting. Python code, data input pipeline. Build a reproducible pipeline for medical inputs by checking the data structure before interpreting clinical values. Then summarize the results carefully while avoiding any exposure of sensitive details. The code imports 3 tools needed for handling data and dates. The CSV module reads and writes comma-separated files. The input-output module supports working with text streams in memory, and the datetime tool converts date strings into date objects for processing. A small set of synthetic medical records is stored as comma-separated text to mimic a patient data table. Each record includes basic fields such as patient details, visit date, blood pressure, glucose level, and diagnosis. This approach simulates reading a CSV file, making it easier to test the data input process without using a real file. We identify the key fields needed for the workflow, including patient identifiers, demographics, visit date, clinical measurements, and diagnosis. Defining these required fields ensures the later data processing supports accurate analysis and reporting. An in-memory file-like object lets a CSV string be read as if it were a real file without saving it to disk. The dictionary reader then processes each row as a dictionary, using the column headers as keys and the row values as entries. This makes the data easy to access and work with by field name. The code checks whether the CSV data includes all required columns. It reads the column headers, compares them with the required fields, and identifies any missing ones. This validation helps ensure the data is complete before further processing. We begin by creating 2 empty lists, one to store cleaned and validated data rows, and another to record warnings. The warnings help track issues such as missing or non-numeric values during processing. This prepares the workflow to clean the dataset while keeping a record of any problems found. The process reads each data row after the header, creates a clean, editable copy of the row, and prepares it for processing. A key step is converting the age value from text into an integer so it can be used correctly in later numerical checks or calculations. The code turns a visit date stored as text into a true date object. It uses the date parsing function from the datetime library with a year, month, and day format, making the date easier to compare and work with later. The code processes key clinical fields, including systolic blood pressure and glucose level, by taking each value from the current data row and removing extra spaces at the beginning or end. This cleanup helps ensure the values are ready for later steps such as conversion or validation. The code validates each raw value by checking whether it is numeric. If it is, the value is converted to an integer and stored for further processing. If not, the field is set to none and a warning records the row and field so data quality issues can be tracked during the pipeline. The code verifies that each row's sex value is either F or M. If it finds any other value, it adds a warning so the entry can be reviewed. This helps catch unexpected or incorrect category values early. The code adds each cleaned row to a collection of clean rows. This builds the final dataset from entries that have already been checked and, if needed, corrected. As a result, the data remains consistent, reliable, and ready for later analysis or reporting. The code summarizes data completeness by first counting all processed records, then counting how many include valid systolic blood pressure values and valid glucose values. These totals show how much usable information is available for the key clinical measurements. Use an empty dictionary to count how often each diagnosis appears in the cleaned data. As each row is processed, extract the diagnosis and increase its count, adding it if it has not appeared before. This efficiently summarizes diagnosis frequencies without using patient identifiers. The Data Input Pipeline Report summarizes key checks on the loaded dataset. It reports the total number of records, any missing required columns, and how many records have valid blood pressure and glucose values. It also summarizes diagnosis counts and the number of input warnings, including a few examples to show the kinds of issues found. This script validates a small set of synthetic medical records from CSV text. It checks required fields, converts ages and visit dates, and flags missing or invalid blood pressure, glucose, and sex values. It then reports record totals, valid measurement counts, diagnosis frequencies, and sample warnings, while protecting privacy by avoiding patient identifiers. Data Processing Pipeline. In a medical data pipeline, raw records must be checked and organized before they can support reliable reports. This means confirming that fields such as patient age, visit date, and diagnosis category have the right names, formats, and values. Careful validation helps catch issues like incorrect lab values or inconsistent dates, protecting the dataset's integrity and supporting accurate interpretation. A robust data processing pipeline separates cleaning, validation, transformation, and summarization into clear stages. Cleaning fixes problems such as missing or duplicate data. Validation checks that values make sense. Transformation makes entries consistent, and summarization produces reporting metrics. This structure makes the program easier to test, explain, and reuse with similar datasets. When working with sensitive medical data, prioritize aggregate summaries instead of exposing individual records, even if the data is small or anonymized. The pipeline should report issues in a way that protects private details while producing clean, consistent results. This lets the final report focus on clear presentation rather than last-minute data corrections. Python code. Data Processing Pipeline. Build a complete medical data pipeline using only fictional, safely summarized records. The pipeline should validate, clean, transform, and then report the data clearly. The code starts by importing pandas and NumPy, two core libraries for data processing in Python. Pandas supports structured data tasks such as cleaning, transforming, and summarizing data frames, while NumPy provides efficient tools for arrays and numerical calculations. Together, they prepare the foundation for a reliable data processing workflow. A small, fictional dataset is created to represent medical encounters, with each patient visit stored as a record containing details such as age, care setting, diagnosis, blood pressure, A1C level, and outcome. The example includes 2 diabetes visits, one in the emergency department and one in outpatient care, with different measurements and outcomes. These records are collected into a list that will be used to build a data frame for later processing. The dataset contains 2 identical records for the same inpatient medical encounter, identified as A03. The patient is 55, diagnosed with hypertension, with a systolic blood pressure of 169 and an A1C of 5.7, and the outcome is improved. These duplicates are typical in raw data and should be handled during data cleaning to support accurate analysis. 2 fictional medical records are added to a dataset to illustrate validation and cleaning in a medical data pipeline. One record contains an invalid negative age, while the other has a missing systolic blood pressure value. Together, they provide simple examples of the kinds of errors and incomplete fields that the pipeline must detect and handle. The medical records are loaded into a pandas data frame so they can be analyzed easily. The dataset is then checked against the expected column names, including fields like ID, age, and setting. Any missing columns are identified and sorted, helping flag possible data issues before further analysis. The code verifies that the dataset contains all required columns by comparing the expected names with the columns actually present. If any are missing, it raises an error and stops execution, preventing further processing until the data has the necessary fields. Start by recording the data frame's initial row count, then remove duplicate records based on the ID column so each entry is unique. Work with a copied version to avoid changing the original data. Finally, compare the new row count with the starting count to see how many duplicate rows were removed. The code cleans the setting and diagnosis columns by removing extra spaces and converting text to lowercase, making the data more consistent for analysis. It then uses a mapping to group specific setting labels into broader categories, such as treating emergency department labels as emergency and clinic as outpatient. The code standardizes the settings column by replacing its values with a predefined mapping. It then defines the valid categories as emergency, outpatient, and inpatient, and counts any entries that do not match these categories. This invalid count can be used later to check data quality or report potential issues. The code converts the age, systolic blood pressure, and A1C values into numeric form using a pandas conversion method. Invalid entries are turned into missing values, so the data can be used safely for later calculations, comparisons, and analysis. The code performs basic data quality checks by counting implausible ages, such as values below 0 or above 120, and by identifying missing readings for systolic blood pressure and A1C. These checks help flag unrealistic or incomplete entries before further analysis. The data is filtered to keep only valid records for analysis. Rows are included when age is plausible, the care setting is recognized, and systolic blood pressure is present. The filtered data is then copied to create a clean dataset for accurate reporting. The data is summarized by first marking each record where systolic blood pressure is at least 140 as high. The records are then grouped by setting to count how many measurements are in each group and calculate the average of this high blood pressure flag. That average is converted into a rounded percentage, showing the share of high systolic cases in each setting. The report summarizes the data cleaning workflow by showing how many input rows were reduced to usable rows after processing. It also reports duplicates removed, invalid age and setting values, and missing systolic and A1C measurements. Together, these counts give a concise overview of data quality and remaining gaps in the dataset. The code introduces a report section on high systolic blood pressure by setting, then displays a summary of record counts and the percentage of high systolic cases for each setting. By presenting only aggregated results in a readable format, it highlights the key patterns without showing individual records or unnecessary detail. This script cleans and summarizes a small set of fictional medical records. It loads the data, checks required fields, removes duplicate patient entries, standardizes text values, and converts key measurements to numbers while flagging missing or implausible data. After removing invalid records, it reports how many rows were usable and calculates the share of patients with high systolic blood pressure in each care setting. The result is a compact overview of data quality and a key clinical pattern. Report generation. Report generation is the final stage of a data workflow, where processed data is turned into clear results for the reader. In a medical dataset, this might mean removing invalid records, calculating averages, and summarizing blood pressure readings. The goal is to present key findings in a readable format so users can interpret the data without manually inspecting every record. A strong medical data report gives enough context to make results trustworthy and understandable. It should identify the dataset or time period, state how many records were analyzed, and clearly separate valid findings from warnings or limitations. Any records removed because of missing or invalid data should be explained, while sensitive information such as names or full medical record numbers should be avoided by using aggregated or de-identified data. Strong reports are concise, consistent, and reproducible. They highlight the main conclusions, use a stable structure that makes results easy to compare, and clearly reflect the processing rules behind the analysis. A useful report typically moves from an overview of the input through quality checks and summaries to interpretations or limitations that turn data into actionable insight. Python code. Report generation. Create a concise clinical report using aggregated, de-identified example data. Keep the workflow clear, readable, and reproducible. We import pandas to work efficiently with structured clinical data, such as tables. We also import the text input and output module to treat in-memory text as if it were a file. Together, these tools prepare the data for reading and processing. We begin with a small de-identified clinic dataset stored as text. It includes patient codes, blood pressure readings, age, and visit status, with some missing values to reflect real-world data. This lets us practice analysis on realistic health data while protecting patient privacy. The clinic data is loaded into a pandas data frame from text-based CSV content. A string buffer makes the multi-line text act like a file, so the pandas read CSV function can parse it safely into a structured format for analysis. The code counts the dataset's records by checking the length of the data frame index, which corresponds to the number of rows. This provides the starting total before any filtering or analysis is done. The code validates adult blood pressure readings by checking that systolic values are between 70 and 220, while diastolic values are between 40 and 130. Readings outside these ranges are treated as implausible and excluded from further analysis. To make age-based summaries reliable, first confirm that every record has an age value. By filtering out entries with missing ages, the analysis uses only complete data and produces more meaningful age-related insights. We keep only records with valid systolic and diastolic blood pressure values and a non-missing age, so the analysis uses complete and clinically relevant data. These conditions are combined with a logical AND, then applied to the data frame to create a separate copy of the valid rows. This protects the original data and supports data integrity while excluding identifiers. The report tracks transparency by counting how many records were left out of the analysis. It compares the total records loaded with the records that met the analysis criteria, and the difference gives the number excluded. This helps show how much of the original data was actually used. A blood pressure categorization function labels each reading based on systolic and diastolic values. Readings with systolic pressure of 180 or higher, or diastolic pressure of 120 or higher, are marked as urgent range. Otherwise, readings with systolic pressure of 140 or higher, or diastolic pressure of 90 or higher, are marked as high range. And all remaining readings are labeled not high range. A row-based category function is applied to the valid records data to classify each patient's blood pressure using their systolic and diastolic values. This creates a new category column that labels each record as urgent range, high range, or not high range according to predefined thresholds. To summarize the blood pressure data, calculate the mean systolic and mean diastolic readings from the valid records. These two averages show the central tendency of the patient's blood pressure and provide a concise overview of the group's overall health profile. This step counts how many valid records fall into each blood pressure category. It uses a pandas counting method on the category column, then stores the results as a dictionary for easier use later. These pelts summarize the category distribution for the clinical report. The workflow builds a blood pressure report as a set of text lines. It includes the report title, the total records received, how many were analyzed, and how many were excluded. It then summarizes average systolic and diastolic pressure, counts records in the high and urgent ranges, and adds a privacy note stating that only de-identified aggregate results are used. The code combines the report lines into one neatly formatted report, with each line separated for readability. It then prints the result to the console, so the user can view the blood pressure analysis summary without exposing patient identifiers. This script analyzes de-identified blood pressure records by loading the data, removing invalid readings and records without age information, and counting the exclusions. It classifies valid blood pressure results as urgent, high, or not high, then calculates average systolic and diastolic values. The final report summarizes how many records were received, analyzed, and excluded, along with category counts and average pressures, using only aggregate results with no patient identifiers. Quality review. Correctness checks. Correctness checks confirm that a program's results match what is expected, not just that the program runs. In medical data workflows, this means tracing data from input to final report and making sure each step preserves accuracy. A report can still be wrong if it mishandles missing data, duplicates, labels, or denominators. Careful testing with known cases and edge cases helps ensure the program's logic supports the intended clinical or research goal. Medical programming requires extra caution because clinical data often contains irregularities such as incomplete dates, mixed units, or records that combine separate visits incorrectly. Programs should be tested against these issues so they do not produce misleading results, like wrong averages or inflated patient counts. The goal is not to fix every dataset, but to make sure the program behaves predictably and its limitations are clear. Correctness checks should confirm both accurate results and responsible data handling, even for small teaching datasets that may resemble clinical data. Outputs should avoid unnecessary identifiers or private details and summarize information rather than exposing row-level records. Review reports to ensure numbers, labels, and wording are clear and useful for clinicians or researchers. Python code. Correctness checks. Review checks compare expected results with actual outputs to confirm performance. Using small teaching data helps avoid sensitive identifiers, while aggregate reporting supports safer interpretation in clinical settings. The script starts by importing pandas, a library used to work with structured table-like data. It will be used to create and manipulate a data frame, which stores information in rows and columns for later processing and analysis. We create a small de-identified dataset where each visit record includes a study identifier, age, diagnosis, and glucose level. The data is safe for analysis because it contains no sensitive patient information. Some diagnosis labels use different capitalizations to help test text normalization later. These lines add 2 patient records to a simulated dataset. One record includes a patient with study ID A2, age 52, diabetes, and a glucose level of 145 milligrams per deciliter. The other adds patient A3 with asthma, a glucose level of 99, and no recorded age. Together, they help test how the code handles missing values and duplicate records. The snippet adds 2 de-identified visit records to a small dataset used for correctness checks. One record is for study ID A4, age 40, with hypertension and a missing glucose value. The other is for study ID A5, age 74, with diabetes and a glucose level of 210. We load the records into a pandas data frame to organize the data in a table. This makes it easier to work with the data and prepares it for key processing tasks such as filtering, aggregation, and transformation. Define the required columns for the data, such as study ID, age, diagnosis, and glucose level, to make sure the dataset contains the fields needed for analysis. Then compare these requirements with the actual columns in the data frame to find any missing fields that could affect the analysis. The code verifies that the data includes all required columns before starting the correctness review. If any are missing, it stops and raises an error explaining the problem, which helps prevent later analysis failures. The code removes duplicate data frame rows using the study identifier, so each patient appears only once. This supports more accurate analysis by treating the patient identifier as the key for uniqueness, rather than relying on other details that may change between visits. The data is filtered to keep only records with complete age, diagnosis, and glucose values. Any rows missing one of these key fields are removed before analysis. The number of excluded records is then found by comparing the original dataset size with the filtered dataset size. The code cleans the diagnosis column by removing extra spaces and converting all entries to lowercase, making comparisons consistent. It then checks which cleaned entries are labeled diabetes and sums those matches. The final integer gives the total number of diabetes diagnoses in the dataset. We first count the complete records, meaning entries with no missing values in the required fields. This count becomes the denominator for the analysis. Then, we find the share of those valid records with a diabetes diagnosis by dividing the number of diabetes cases by the total complete records and converting the result to a percentage. This shows the prevalence of diabetes in the cleaned dataset. The process sets expected counts as benchmarks for checking the data, including unique records, complete records, and diabetes cases. It then creates a set of true or false checks to confirm that the number of unique records is 5 and the number of complete records is 3. These checks help verify that the data processing results match the expected values. The code validates the dataset by checking whether the actual number of diabetes diagnoses matches the expected count. If the two counts are the same, this check passes and supports the overall data quality review. The correctness review summary reports how many unique records were checked, how many were excluded for missing required values, and how many complete records show a diabetes diagnosis. It also gives the diabetes percentage among complete records, rounded to 1 decimal place. Finally, it reports whether all correctness checks passed as a true or false result. This script checks a small set of de-identified medical records for data quality before analysis. It verifies required fields, removes duplicate study records, excludes incomplete entries, and standardizes diagnosis labels. It then calculates the number and percentage of complete records with diabetes and compares the results with expected values. The output summarizes the cleaned records, exclusions, diabetes cases, and whether all checks passed. Readability review. Readable code should be easy for someone else to understand, maintain, and troubleshoot without the original author. In medical data workflows, this is especially important because confusing code can lead to errors or misinterpretation. Keep the workflow clearly organized with meaningful names and distinct stages for tasks such as reading data, checking quality, transforming fields, and preparing reports. When working with sensitive medical data, readable programs make privacy protections and data handling decisions clear. The workflow should clearly indicate when data is fictional or de-identified and where sensitive details are excluded. It should also show that the program summarizes patterns, such as age groups and conditions, rather than making individual diagnostics. Comments should explain important choices, like separating records with impossible dates, without stating the obvious. When reviewing a program in a team setting, focus on whether it is easy for clinicians, researchers, and analysts to understand. The code should have a logical flow, consistent naming, and brief explanations that match the analysis. Treat the review as a clear narrative of the data, transformations, results, and limitations. Good readability builds trust, supports accurate interpretation, and makes responsible reuse safer. Python code. Readability review. In a medical workflow, readability supports safe maintenance by making names and sections clear and easy to follow. Outputs should also protect privacy by avoiding sensitive record-level details. The script starts by importing pandas, a library used to work with tabular data. This gives the code access to DataFrames, which help organize, process, and summarize the medical records dataset efficiently. A small, de-identified teaching dataset is created to protect privacy while supporting analysis. Each entry represents a medical record, including an age group, a condition such as diabetes or hypertension, and a health outcome such as improved or stable. The snippet adds 2 de-identified teaching records to the dataset, one for a person aged 40 to 64 with diabetes and a stable outcome, and one for a person aged 18 to 39 with asthma and an improved outcome. These records support analysis without including sensitive personal information. We create a pandas data frame from the records list to organize the visit summary data in a clear table. This structure makes the data easier to filter, summarize, and analyze, supporting the readability checks and later summaries in the workflow. First, define the required data fields, such as age group, condition, and outcome, to make sure the dataset supports the analysis. Then compare these requirements with the columns in the visit summary table to find anything missing. This helps catch data gaps that could affect the workflow's accuracy and readability. The code verifies that the data includes all required columns before continuing. If any are missing, it raises an error that identifies them and stops the workflow, helping prevent later problems caused by incomplete data. The code summarizes the dataset by counting how often each condition and each outcome appears. It sorts these counts by name to keep the results in a consistent order. These summaries show the overall distribution of conditions and outcomes while protecting individual record details. A readability checklist is created to confirm that the workflow is clear and safe. It verifies that the purpose is clearly stated, names are meaningful, sensitive fields are excluded, and the output is limited to aggregate reporting. Together, these checks help maintain clarity while preventing individual level or sensitive information from being exposed. The code measures readability by counting how many checks passed and comparing that number with the total checks performed. It does this by treating past results as true values, then using the total number of criteria to summarize overall workflow readability. The code performs a readability review of a de-identified teaching workflow. It reports the number of records, confirms whether all required columns are present, and shows how many readability checks passed. It also summarizes condition and outcome counts, then concludes that a clear workflow structure supports safer review and reuse. This script checks whether a de-identified medical workflow dataset is complete, readable, and safe to review. It verifies required fields, summarizes conditions and outcomes in aggregate, and applies a checklist for clear purpose, meaningful naming, privacy protection, and aggregate-only reporting. The output reports the rows reviewed, confirms the required data are present, shows how many checklist items passed, and concludes that the workflow structure supports safe reuse. Correctness check. A correctness check confirms that a program does what it is meant to do, not just that it runs. In medical data workflows, this means ensuring information stays accurate from input to final report, including how fields are read, missing values are handled, duplicates are counted, and percentages are calculated. Reviewers should make sure the results match expectations and handle edge cases so the report is reliable for research or clinical use. Check your program with small test cases where the expected result is clear, and manually verify a few records before using the full dataset. Handle missing data with consistent rules, either by excluding it or flagging it for review. This is especially important in medical data, where processing choices can change the interpretation of results. Program correctness requires more than accurate calculations. It also means handling imperfect and sensitive data responsibly. In medical datasets, programs should detect errors such as inconsistent labels, unrealistic values, or impossible dates. They must also protect personal information. A correct program supports reliable interpretation while respecting the people represented by the data. Python code, correctness check. Use small medical examples to check correctness, verifying the expected answers before reporting results. Any sensitive identifiers should be removed from the output. The script starts by importing pandas, a library used to work with structured, table-like data. This gives the code access to DataFrames and tools for common data analysis tasks, such as filtering, aggregation, and statistical calculations. We create a small de-identified dataset as a list of medical visit records. Each record stores a patient identifier, age, systolic blood pressure, and lab result. The data includes one missing lab value, one likely invalid age of 200, and a duplicate record, making it useful for practicing basic data review and cleaning before analysis. The code converts a list of records into a pandas data frame, organizing the data into a table for easier analysis. This structure supports efficient tasks like filtering, aggregation, and statistical checks used later in the script. We first specify the key columns the data must contain: ID, age, systolic, and lab. Then we compare this required set with the columns actually in the data frame to find any missing fields. This helps catch structural problems before running later calculations. The code verifies that the data includes all required columns before analysis continues. If any are missing, it raises an error and stops execution, helping ensure the data is complete and safe to use. The code checks for common data quality issues by counting ages outside the valid range, duplicate records with the same identifier, and missing lab values. These summary counts highlight records that may need further review or cleaning. We clean the data by keeping only records with valid ages from 0 to 120, using a range check on the age field. After making a copy of the filtered data, we remove duplicate patient records based on the patient identifier. This leaves one valid record per patient and helps prevent repeated entries from biasing later analysis. First, count the cleaned patient records to get the denominator for later calculations. If no valid records remain, raise an error to show the dataset is insufficient for analysis. This protects all following calculations by ensuring they are based on valid patient data. Identify patients with elevated systolic blood pressure by counting those with values of 140 or higher. Then calculate their percentage among all valid patients and round it to 1 decimal place. Finally, average the available lab values while ignoring missing data and round the result to 2 decimal places. The code sets expected results for the denominator, elevated systolic count, and missing lab count, then uses assertions to compare those expectations with the actual outputs. These checks confirm that there are 3 valid unique patients, 1 patient with elevated systolic pressure, and 1 missing lab value. Together, the assertions serve as simple validation points to ensure the data processing matches the known manual results. The report begins with a clear header, then summarizes the filtered patient data. It shows the number of valid unique patients, the count and percentage with elevated systolic blood pressure, and the average lab result after excluding missing values. It also reports records flagged for bad ages, duplicates, and missing labs, while confirming that no direct identifiers or sensitive details are included. This script checks a small medical records dataset for required fields and flags data quality issues such as invalid ages, duplicate records, and missing lab values. It removes invalid and duplicate entries, then counts patients with elevated systolic blood pressure and calculates the average lab value for valid records. The results are compared with expected values, and the final report summarizes key counts and flagged issues without exposing sensitive identifiers. Result presentation. Summary findings. Summary findings help turn a completed Python data workflow into clear clinical or research insights. A good summary highlights the main patterns in plain language, such as common patient characteristics, frequent health measures, or differences in follow-up. It should give a concise overview without examining every data point, and it should describe observed patterns carefully without implying causation. A strong summary should give stakeholders the key results, the population studied, and the main limits of the data. In medical contexts, this means reporting important patterns, such as differences in wait times or patient groups, while noting uncertainties like short time frames, missing factors, or small sample sizes. The goal is to be clear and concise, because too little caution can mislead decisions, while too much detail can hide the main insight. When reporting medical data, protect privacy while keeping the statistics clear. Avoid details that could identify individuals, especially in rare cases or small groups, and summarize broader patterns instead. Group rare diagnoses when needed and use neutral, respectful language to support responsible interpretation and trust in the data process. Python code. Summary findings. Summaries help turn workflow outputs into clear interpretation. They should use small, privacy-protecting examples and present concise findings that support responsible medical decisions. The script starts by importing the pandas library, which is used in Python to work with structured data such as tables or spreadsheets. This makes pandas tools available for creating and manipulating DataFrames, the main pandas structure for tabular data analysis. We create a small, de-identified medical dataset to simulate patient records while protecting privacy. Each record includes age, systolic blood pressure, a broad diagnosis group, and whether follow-up was completed. The example uses cardiometabolic patients with different blood pressure values and follow-up outcomes, without including personal identifiers. This segment builds a small, de-identified patient dataset for analysis. It adds 3 medical records with each patient's age, systolic blood pressure, diagnosis group, and whether follow-up was completed. The records include respiratory, cardiometabolic, and other diagnosis categories, with follow-up completed for 2 patients and not completed for 1. This snippet represents part of a de-identified medical dataset, with each record describing the patient's age, systolic blood pressure, diagnosis group, and whether follow-up was completed. The examples include patients in cardiometabolic, respiratory, and other diagnosis groups, with follow-up status varying across records. The data supports analysis of medical trends while protecting patient privacy. The code converts a list of medical records into a pandas data frame, organizing the data into rows and columns for easier analysis. Each record becomes a row, with its fields used as column names and values placed in the matching cells. This structured format supports later tasks, such as filtering, grouping, and statistical calculations. The code defines the essential columns needed for the analysis, such as age, blood pressure, diagnosis group, and follow-up status. It then compares these requirements with the columns actually present in the data. Any required columns that are missing are collected so the program can flag incomplete data or handle the problem appropriately. The code verifies that the data frame includes all required columns before analysis continues. If any are missing, it raises an error that identifies them, helping prevent later workflow problems. The code first checks whether the dataset has at least 3 rows. If it is smaller, it raises an error to stop the analysis because there is not enough data to create a meaningful summary. These calculations summarize key clinical metrics by converting simple true or false checks into percentages. They measure the share of visits by adults age 65 or older, the share with systolic blood pressure of at least 140, and the overall rate of completed follow-up. Together, they provide a quick overview of important patterns in the dataset. Group the data by diagnosis group and calculate the average follow-up rate for each category. Then identify the category with the lowest average follow-up and convert that value to a percentage. This highlights which diagnosis group may need more attention in follow-up care. This summary reports exploratory findings from a small, de-identified sample of visits. It includes the sample size, the share of visits by adults age 65 and older, the share with systolic blood pressure at or above 140, and the overall follow-up completion rate. It also identifies the diagnosis group with the lowest follow-up rate. Because the data are limited and privacy protected, the results should be interpreted as observed patterns, not causal conclusions. This script uses pandas to explore a small, de-identified medical dataset. It first checks that key columns are present and that there is enough data to analyze, then summarizes patterns such as visits by older adults, elevated systolic blood pressure, follow-up completion, and the diagnosis group at the lowest follow-up rate. The output is a brief, privacy-conscious summary of observed trends, without making causal claims. Clinical interpretation. Clinical interpretation explains what program results mean in context, not just what the metrics show. It connects findings to the dataset's limits, such as small sample size, so results are useful without being overstated. For example, a higher average blood pressure among older adults may suggest a trend, but should not be treated as strong evidence if the data is limited. Clinical data should be interpreted in context, connecting results to possible, real-world meaning without making unsupported medical conclusions. High glucose values, for example, may need further review, but do not by themselves confirm a condition. Missing fields, such as smoking status, may signal bias in the data rather than a patient characteristic. Accurate interpretation depends on both technical and health context, including where the data came from. When presenting medical results, protect privacy by using general language and focusing on patterns rather than identifiable individuals. Keep a professional tone, especially when discussing serious conditions or disparities, and tailor the message to the audience. Clinical audiences need clear next steps, such as validation or follow-up review, while researchers need context about sample size, definitions, significance, and precautions. Python code, clinical interpretation. Clinically interpret summarized workflow results using aggregate language to protect privacy. Clearly state any uncertainty before recommending next steps. We begin by importing pandas, a key library for working with tabular data. It supports tasks such as creating DataFrames, calculating statistics, and handling missing values, which are needed to process the clinical visit data in a structured way. We create a small sample dataset to represent patient visits, with each patient stored as a set of values, such as age, systolic blood pressure, glucose level, and smoking status. The example includes 2 patients with different health measurements and smoking histories. This gives us a simple, manageable dataset for basic analysis. 2 additional patient records are added to the simulated dataset before converting it into a pandas data frame. One patient is older with higher blood pressure and glucose and does not smoke, while the other is younger with lower values and an unknown smoking status. These examples help make the dataset more varied for exploring different clinical scenarios. First, the records are converted into a pandas data frame, so the data is organized in a table for easier analysis. Then, the total number of visits is found by counting the data frame rows. This prepares the data for later validation and summary checks. We first identify the required data fields: age, systolic, glucose, and smoking. Then we compare these requirements with the data frame's actual columns to find anything missing. This check ensures the needed columns are present before continuing the analysis. The code verifies that all required clinical fields are present before analysis begins. If any are missing, it raises an error and stops the program, preventing incomplete data from producing unreliable results. We flag patients aged 65 or older, and those with systolic blood pressure of 140 or higher. These masks help identify older patients and possible blood pressure concerns for further clinical review. To compare systolic blood pressure by age group, calculate the average systolic value separately for people aged 65 or older and for those under 65. This gives a simple group-level comparison between older and younger individuals while avoiding identification of any specific person. The code counts 3 types of records that may need clinical review: patients with systolic blood pressure of 140 or higher, patients with glucose levels of 126 or higher, and patients with missing smoking status. These totals summarize key health risks and data gaps for follow-up. The output summarizes clinical patterns from the simulated visit records, including the total records reviewed, average systolic blood pressure for older and younger groups, review flags for blood pressure and glucose, and missing smoking status counts. It highlights a possible higher blood pressure burden among older visits, while emphasizing that review flags are not confirmed diagnoses. Because the dataset is small and simulated, the results should be interpreted cautiously, with validation and aggregate pattern review as the next step. This script analyzes a small simulated clinical visit dataset, first confirming that key fields are present. It compares average systolic blood pressure between older and younger patients, flags elevated blood pressure and glucose, and counts missing smoking status values. The results suggest higher blood pressure among older individuals and identify records needing further review. Because the dataset is small, the findings should be treated cautiously and validated with further analysis. Summary findings. A strong findings summary turns processed data into clear insights by explaining what was observed, why it matters, and how confident the results are. For small medical datasets, it should focus on key patterns, such as how many patient records were analyzed or excluded, and the main trends in age or diagnoses. This helps readers understand the evidence, its limits, and the meaning of the results, without having to reconstruct the full analysis themselves. When reporting results, use careful, precise language, especially with sensitive data. Present findings as observations rather than broad conclusions, and avoid overstating what small or specific datasets can show. Protect privacy by summarizing patterns without exposing identifiable details, so the analysis remains useful and ethically responsible. A strong summary should connect data processing to clear, useful insights. It should state what was analyzed, what was found, and what reasonable next steps follow, such as reviewing flagged clinical records or studying research trends further. It should also note key workflow issues like missing data handling or exclusions that may affect interpretation. Overall, the goal is to reduce complexity while preserving the information needed for sound decisions. Python code summary findings. Effective summaries should be concise, clear, and easy to interpret. Aggregating data helps protect privacy while still supporting useful analysis, and validated records make the resulting findings more trustworthy. The script starts by importing the pandas library, which provides tools for working with tabular data. This enables the code to create and manipulate data frames for the data analysis that follows. A small sample dataset is created to represent patient encounters. Each patient record includes an ID, age, diabetes status, and systolic blood pressure. The 3 example records provide a simple structure that can be used for later data analysis. The snippet adds 3 simulated medical records used to analyze health metrics with missing data. They include 1 record with a missing age, 1 with a missing systolic blood pressure value, and 1 complete record for an older adult with high systolic pressure. Each record includes an ID, diabetes status, and available blood pressure information. We convert the list of record dictionaries into a pandas data frame so the data is organized as a table. Each dictionary becomes a row, and its keys become column names, making the dataset easier to work with and analyze in pandas. The code identifies the required report fields: age, diabetes status, and systolic blood pressure. Only records containing all of these values are treated as valid, helping keep the analysis complete and reliable. The code creates a clean subset of the data by removing rows with missing values in the required fields. It uses the pandas drop missing values method on those selected columns, then copies the result into a new data frame so the original data stays unchanged. To make the analysis transparent, the code counts how many records were left out. It compares the original total with the number of valid records, showing how many were excluded because required report fields had missing data. This adds a new Boolean column to the data frame that marks whether a systolic blood pressure value is 140 or higher. The flag makes it easier to identify clinically important high systolic readings and quickly estimate how common they are in the dataset. The code summarizes the valid dataset by counting complete records and key health indicators. It reports the total number of valid records, then counts how many people are age 60 or older, how many have documented diabetes, and how many have high systolic blood pressure. These counts provide a quick overview of the dataset's age, diabetes, and blood pressure characteristics. The code calculates key dataset percentages by dividing each relevant count by the total number of analyzed records and multiplying by 100. It applies this to the share of adults age 60 or older and to records with high systolic blood pressure, making the dataset's characteristics easy to interpret. The summary reports key findings from the simulated encounter records, including how many records were analyzed and how many were excluded for missing data. It highlights the share of adults age 60 or older, the number with documented diabetes, and the count and percentage flagged for high systolic blood pressure. These results apply only to this small dataset, and no individual patient details are disclosed. This script uses pandas to analyze a small set of medical records while protecting privacy. It removes records missing key information, then identifies valid entries with high systolic blood pressure, defined as 140 or higher. It reports aggregate counts and percentages for people age 60 or older, people with diabetes, and people with high blood pressure, with results limited to this dataset. In this lecture, you learn to build a complete Python program that processes a small medical dataset from input to report output. Evaluate the program for correctness, readability, error handling, and appropriate handling of sensitive examples. And present the workflow results in a concise form that supports clinical or research interpretation. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.